All right. Okay, so we got to clean up our slides from last time, and then we'll get into today's slides proper. So anybody have any questions up until this point? I'm not going to go through steps 1 through 4 again. We went through those pretty thoroughly last time. But we'll pick up, I think I'm at the first slide for step 5. So we'll start at the beginning of step 5. I think that's roughly where we got last time. And we'll try to plow through this and get through most of it. There's even a whole week of OAuth. I don't have enough time to go over everything I want to talk about. So we won't get through all of Friday's content. But it's not on the homework, so no worries. Okay, any questions getting up to speed? Let's effing do this then. Okay, so we have an authorization grant from the user. So we have an authorization code that we need to cache in for an access token. And the access token is what we'll actually use to access the database on behalf of our users. So we want to cache in this authorization code. To do that, the server is going to need a few things. The big thing is it's going to need to authorize us. It's going to need to say that this is the actual legitimate client. And it's going to check the code to authorize the user and say, is this a code that I actually gave a particular user for your app? So let's do that. And we get to use HTTP for this. Or HTTP. We've been using HTTP. But we get to use direct communication. We have to use direct communication with the API at this point. So instead of going through the user as a liaison, we're going to go directly to this third-party API, which means we have all of our tools available to us. We don't have to use redirects and URIs and query strings. We can do whatever we want, including posts and put content in the body of the post. Custom headers, we can set whatever headers we want because those won't be tampered with by the user. So we get to do whatever we want here. And I recommend using the requests library. I put this right in the homework document. Use the requests library. It's the easiest way to get this done. And it's allowed, so use it, take advantage of it. The request library is going to let you specify the method, the path, and the content that you want to send. And it'll do content length, content type, all the other things for you. It's going to do that stuff for you. And you can set custom headers with it. It's powerful. It's powerful and easy to use. So all of the steps in 1 through 4 can be mimicked by an attacker. So nothing at all can be trusted. This authorization code that we have, nothing about it can be trusted because everything, steps 1 through 4, could have been compromised. No guarantee of anything there, at least the way we have things set up right now. So now we need to actually verify things and say, hey, auth server, we are this app, this is legit, it's from me, and we do that by sending the client secret. The client secret never is involved with any step of the process except this one when we're talking to the API directly, when our app is talking to the API. The user never handles our secret. Nobody else handles our secret. So we do keep this secret. We do everything we can to keep it secret unless we have a database compromise or something, or server itself is compromised. This secret should be secret. So the possession of this secret does verify that we are who we are. It authenticates us effectively as a big, long, high-entropy password is what the secret's doing for us. And we're going to send it through the authorization header. We're going to start using this authorization header in these steps. So in the authorization header, we're going to set an not on this slide, but we'll get to it in the next slide. Through the authorization header, we're going to send this client secret, and we're not going to send it in the body or in the URL. It's strongly recommended by the RFC to put it in the authorization header. It does allow, barely allows for you to send it in the body of a request, but it says only send it in the body of the request if you have no access to your headers, if you can't control your own headers, which are unique situations, which are not the situations we're in, and not the situations Spotify's in. So Spotify says, slap that thing in the authorization header. And the RFC says you absolutely cannot send it in the URL of your request. Do not send it in the URL. That's too dangerous for sensitive information to be in a URL. One example is if you have a logger anywhere in this process, Maybe you're behind a reverse proxy, and the reverse proxy has logging enabled. It doesn't even have to be your code doing it. They'll usually log the URLs of every request and response. It'll put the URLs, request. It'll put the URLs in log files, and you don't want your client secret sitting in a log file somewhere. But it's not going to log headers or the body of those requests, just the path generally. You might get an aggressive logger, and you got to watch out for that. But generally, they'll store just the URL. So we don't want those sensitive information in the URL sitting in a log file somewhere. It's one way that can go awry. And for the Spotify API specifically, it wants this exact string. It wants this base64 encoded string with client ID : client secret. Different APIs, they will want the secret as an authorization header. They won't all ask for the client ID and secret in this exact format, but this is the one the Spotify API sends. So this is one of our Spotify-specific portions of this. They'll almost all use the authorization header, but Spotify wants this format. So let's talk about this format. Bless you. Since you do have to do this on your homework if you're doing the AOs, let's talk about how to actually compute this. This is one of the trickier parts of using the Spotify API is to compute this value. And I recommend, I'll say strong, I feel like I never recommend anything. I always strongly recommend it. So I'll just recommend this one. If you don't do this, I don't know, you risk losing an AO. It's not the worst thing. It's not like an LO where you're going to fail. But I'll recommend doing this where using this as a test case, I have the actual values that I punched all these in and made sure these are the actual values that you can use as a test case and test a method that you write that takes the ID and secret and computes this value. I'd recommend doing that. But if your client ID is ABC and your client secret is 123 as a string, not an int, I kind of wish I put at least one letter in this one to make it very clear that it's a string. But I got the double quotes around there, so it should be clear. And then we're going to compute client ID : client secret, which is this literal string. ABC, the client ID, the character : and then 123, the client secret in this case. Obviously, with your actual client ID and client secret, don't use ABC 123. And then we're going to base64 encode this, which for this value, ABC : 123, should be this exact value if you're using base64 encoding. Base64, I don't want to go deep into what the encoding is, but just very briefly, it's a way to encode any arbitrary bytes as an ASCII string. And these are going to be URLs. Oh, I can't even say that. Not really URL safe because it's got the equal signs. But it's going to be safe to put in a header. It's all ASCII characters, so it can be in a header, and that's where we're putting this value is in a header. So this is the right encoding. But if it were arbitrary bytes, those arbitrary bytes are not necessarily going to be UTF, proper UTF encoding stuff. So base64 is what we're using to make sure we can put random bytes as a string, encoding random bytes as a string. And when you're using base64, it does work in bytes, so make sure you're encoding and decoding whenever appropriate. So we have a string. We have the string ABC : 123. As a string, we want to encode that into bytes, take the base64 encoding of those bytes, and then encode that base64 into a string, back into a string. So we're going to encode, base64, decode. Did I say that right? Yeah, and then decode whatever base64 gives you, decode that back into a string, and then you're going to set that as your header with this exact syntax. Authorization is the header name, : basic, with this optional space here, basic space, and then the value for that header, that value that you computed containing your base64 encoded client ID and client secret. So very important, probably the most complex step. The rest of this is just, there's so many steps, but out of all the steps, this is probably the most complex part of it, and it's not that complex, but there's just so many steps that by the time you get here, it'll feel like a lot. Okay, and then we're going to ship that. We're going to send that to the API as the header, and then in the body of this post request that we're forming, so we set a custom header just there. Now we're going to set the body equal to these parameters. We'll send these three parameters, the grant type, which is part of the RFC. It defines grant type. It's grant underscore type, all lowercase letters. That'll be set equal to authorization code, this exact string, because we're caching in an authorization code for a token. Then code, which is the actual code itself. And then the redirect URI, which must match the exact URI that you used for the authorization request. That exact redirect URI has to be there. If it's not character for character identical to the redirect URI that you used when you had the authorization grant, then the server is going to say, something's up here, something's wrong, and it's going to reject your request. And of course, the code has to be valid. The client ID, the client secret, everything has to be valid, everything has to check out. The authentication server gets all of this information as a URL encoded string. So we get to use post requests, and this will vary from API to API, but the Spotify API will use URL encoding in the post request. So you're taking those three parameters from the previous slide, this grant type code and redirect URI, putting them in effectively a query string, but instead of putting it in the URL of a GET request, you're putting it in the body of a POST request, just like our HTML forms did when we switched GET to POST and didn't change anything else. That's what we ended up with. So we're sending that in the body of a POST request in the same format as a query string. That's URL encoded. That means percent encoding is important again. But luckily, response type, that's all just characters. Those are all valid URL characters. The code, at least for Spotify and for really any API worth its salt, should be all valid URL safe characters, so nothing there. And then the redirect URI, this is the one that we have to make sure we percent encode. But guess what? You already did that in step 1. So take that exact string that's already percent encoded, and that's your redirect URI. Again, you've already computed that, so there's no work to really be done to make sure that this is all URL safe. But it does need to be URL encoded. Is the client secret the same as the param we requested? I'm not quite sure what you mean by param we requested, but the client secret is when we registered the app. When you go to Spotify's website, to their developer dashboard, and register your app, that's where you get your client secret. And that's the only time you get it, and the only time you use it is when you're talking to the API itself. So we only get it when we register our app, not when we request it over like an API, like an HTTP request to the API during any of these steps. Client secret would be like step -1 in this process, obtaining the client secret. Then we send this as a post with our custom header for the authorization and the body URL encoded grant type code and redirect URI. The server is going to get all this stuff on its token. We're going to send it to the token endpath. The path is actually specified by the RFC, so this isn't just a Spotify thing. It's going to be the /token path of the auth server. We're going to send this request to /token with that custom header and those 3 values, and the server going to think about it. It's going to say, okay, client secret, are you who you say you are? It does this code match? Is the redirect URI match? As long as everything checks out and everything's good, it's going to send you an access token. If anything's bad, it's going to send you usually a 403 and say, hey, you can't do this. Or maybe a 401 if your client secret doesn't check out at all. It's going to send you some 400 level response, which would be pretty vague and cryptic. And if you're anything like me, you're going to go absolutely insane saying, why, what did I do wrong here? Because it's just going to say basically error. And then you have to look through all your code and figure out where you had one character off. So, or you're not as bad as I am, and you don't have to go through that. But if everything checks out, you're going to get your access token. And the format can vary again. For some reason, Spotify uses URL encoding when you're sending this request, but it's using JSON when in its response. So it's going to return a JSON string that's representing a JSON object with a key for access token. It's also going to have a refresh token, which I say topic for another lecture, but that lecture is today. We're just cleaning up Wednesday slides right now. So an access token and a refresh token. And access token is the one we're interested in for AOs 1 and 2. We're not going to use the refresh tokens for reasons I'll talk about when we get to that topic. So in AO1, what would be the client secret? You're going to go to Spotify, you're going to register your app, and it's going to give you a client secret. If you're asking that question, you probably haven't started AO1 yet. There's a link to the Spotify documentation in AO1. I think I link right to the dashboard, if I'm not mistaken. Go to the developer dashboard. If not, Google Spotify Dev or Spotify API. Either one's going to get you where you want to go. And register an app. And when you register your app, that's when you get your client ID and client secret. So at this point, you're going to get your access token. And now, with this access token, we can start connecting to this API on behalf of our users. Whenever we send a request to the API, and most APIs are going to do this, Spotify included, is going to ask you to put that token in an authorization header of type bearer. Bearer meaning that we are a bearer of this token. We possess this token, so therefore we are authenticated because we have possession of the token. And then the user's access token as the value of the bearer authorization header. Once it sees this header, then it's going to say, okay, we're good. It's going to double check this. This is the only value checked. It's going to say, okay, we're good. This is a valid token. And then it's going to serve up some private data. And notice that we can't use cookies for this. Okay, we can't use cookies at this step. Because before, like the access token, it's kind of acting as an auth token. And auth tokens we set as a cookie. And we're not doing that here. We're using an authorization header. And I want to talk about why just for a moment. And if we think through this, it should make sense. We can't use that as a cookie because these requests are coming from our app. Our app and going to the API. And in the diagram, it looks nice and clean. We have a user. We're going to set that user's access token as a cookie and send requests over here. But in reality, we're going to have more than one user. Well, hopefully. We're going to have more than one user of our app. If we have 1,000 users, are we going to have 1,000 cookies and send them all to the API on every single request? I don't think so. So what we're going to do is take their access token, store that in a database, and when one particular user wants to make a request, we're going to pull their access token, set it as a header, as a one-time use header, that we're going to set each time they want to use the API, and send that request over to the API. Makes much more sense there. It's much cleaner. And we're sending requests from a server. We don't have a browser. There's no browser involved at all. So how are we even going to manage our cookies? Like, we're going to have to do that. We'd have to write all the code to say, oh, we got a set cookie header. Let's set this cookie and store. We'd have to do all that browser stuff. Cookies are a browser thing. It doesn't really make sense to use them for server-to-server communication anyway, even if we only had one user. So we're going to use the authorization headers, which is a cleaner way of solving this problem when we would have many cookies or changing our cookies for every single request. Cookies are just headers, so at that point we're doing the same thing as the authorization header, just with a header named cookie instead of a header named authorization. And the authorization is the much more proper way to do it. Okay, and after all that, how do we actually do the application objectives? And I'll say right now is if you're going through this, everything we went through for like a lecture and a half, well, 2.5 lectures almost, everything we went through, that's part of AO1 and AO2. You have to do that process to do either of them. So just to do AO1, you got to go through all of that. And if you're going to go through all of that, please, well, for your own sake, I don't care that much, but for your own sake, do AO2 also. After you get AO1 done, after you go through this whole process, actually doing the final wrap-up pieces, which is login with and then putting the song the user is currently listening to in their chat messages, is like almost no work by comparison. So if you're going through all this process and getting to this point right here, please get AO1 and AO2. Everybody on this, I would expect everybody to either get 0 AOs, because maybe you said, man, this whole week just made my head spin. I'm not even going to try. Let me just focus on the LOs, which is perfectly fine. Or you're going to get both of them. You're going to go through this whole process and get both AOs. Nobody should be getting just one of these AOs. I would be shocked if anybody in the class did, unless it would have to be some really weird situation to get just one of these AOs. So please get 2. So let's go through how to actually do the AOs. Once you have the access token, the AOs are straightforward. We're going to access the API, and for login, we want to access the API and ask for some private information about the user. And for our purposes, we're going to use an email address, but really any way to uniquely identify the user is going to be fine. As long as we can uniquely identify them, email address is perfect. We like email address because they are unique. And they are globally unique. Everybody has a different email address. So it's a perfect, unique identifier to use on the internet. So before this point, steps 1 through 6, if you look really carefully, at no point during any of that do we know anything about this user. We don't know anything about them. We might know through some other means. They might have registered through our app or interacted with our app. We might have been able to gather a little bit of information about them. But through this process alone, we know nothing about them. We know that they clicked a button on our site, and then we got an authorization grant from them, which is a big, long code that doesn't mean anything to us. Just looks like a random string. Has no identifying information about the user. We cached in that code for an access token. The access token is opaque as well. It has no identifying information about the user, at least not that we can read. It might have some information that the API can read, but we would need their encryption keys to be able to read that. So we don't know anything about the user yet, but now that we have an access token and can access the API on their behalf, we can ask the API, hey, who is this? Who is this anyway? So we go to the API and hit an endpoint to get their profile information, which we have to make sure we asked for the proper scopes to be able to access this endpoint. So we access that endpoint and say, who is this anyway? We get their profile information back, and for our purposes, we're going to pull their email out of that. The Spotify API is going to return a big old JSON object again. All the responses are going to be JSON. We love JSON over the internet. I don't know why it uses URL encoding for the authorization grant, but everything else is JSON. It's going to return a big JSON object, pull the email from that object, and now you have the email address for this user. Now that you have their email address, at least the email address that they used when they registered for their Spotify account, now that you have a way to uniquely identify this user is really what we're after. We can go through the registration and login process for them. So we're going to go through the registration process. We're going to create an account for them with their email address that we pulled from Spotify. That's going to uniquely identify them. And they're not going to have a password. They do not have a password. Please note, this should be self-explanatory, but please note that this is different than the empty string as a password or any password is acceptable. Nobody should be able to log into their account with any password at all, ever. It just should not be allowed at all. If you do store empty string as their password in the database, that should actually do it because bcrypt is you're going to call check password on empty string and bcrypt's going to panic. It might actually crash, so maybe that's not the best idea. But whatever you're doing for your logged in with Spotify users, don't allow password login. And then for the login part of the process, you're going to issue them an auth token just like usual. You're going to issue them an auth token, store a hash of that auth token, set the unhashed token as a cookie, store that auth token. You're going to store 3 things: the auth token, their ID, which is their email address for Spotify, and their access token in the database. And then whenever you see that auth token, you're going to look up their record and grab their email address, which is their username in this case, and their access token so you can make more API calls on their behalf. Now, when somebody's logging in, you should also check if they've already logged in. If they already have an account and they're logging in for the second time, once you go through the whole process, you go to the API, you get their email address, look up that email address in your database and see if they've already logged in. Don't destroy their whole account and create a new one every time. If they've already logged in before using that a third party, then use their existing account, which I guess we'd end up replacing all the values anyway. You're going to generate a new auth token. You just got a new access token. I guess in this specific case, it wouldn't harm anything. But you should use their existing account in the real world for sure. And store their access token. If you don't store their access token, you're going through all of this every single time they go to your site, which honestly isn't even the worst thing because it will be invisible to the user. They still just click one button. But if you store their access token, then whenever they do something on the app, which for our purposes is sending a chat message, so AO2, I have almost nothing to say about, except this. For AO2, whenever a user sends a chat message, check if they're a Spotify user. If they're logged in with Spotify, go to the database, you're checking their auth token, that's all you have. Hash the auth token, look up that hash in your database, pull their account, and if there's an access token there, then this is a Spotify user. Use that access token to hit the endpoint that gets their playback state. Get their playback state, it's going to give you this big old JSON object with all kinds of information. Pull the title and artist of the song they're currently listening to from that JSON object and add that to their chat message. If they're not listening to anything, if there's no active player, you're going to get a 204 no content response. So make sure you're not getting JSON decoding errors if the user isn't listening to anything. If there is a response, then decode it with JSON and grab the title and artist. If not, have something that says, okay, they're not listening to anything. Either don't add anything to their chat message or add not listening to anything in their chat message. So once you go through this whole process, AO1 and AO2 are both a similar difficulty after all of this, after all steps. I guess steps 1 through 6. Steps 7 and 8 are pretty straightforward once you start actually accessing the API in their behalf. Getting set up to be able to do that, not so much. That's quite a bit. And notice that these tokens and the refresh tokens that we're about to talk about, access tokens and refresh tokens, kind of got to be stored in plain text. You can't hash these things in your database. These can't be protected in the same way that we protect passwords and auth tokens. So they can just be stored in plain text in your database for the homework. That's fine. And we just got to be super careful. Like, just be careful with them, I guess. Not much we can do. One thing we can do to limit the risk is only ask for the scopes that you need. Don't ask for permission to access things that you're not actually going to need from the user. Just ask for what you absolutely need. So if an access token is compromised, the attacker can't get more than they have to get. And then if you change your scopes later, just ask the user to re-authenticate. They'll have to click agree again on Spotify. It's not the worst thing. But don't ask for scopes that you don't need. Okay, everyone good with that? This is everything you need for AO1 and AO2. We obviously did the LOs already last week. This week was AO1 and AO2. And we'll get in, this is my last slide for Wednesday's lecture. Holy crap, it took half of this lecture too. There's so many details here. But everything we're talking about for today's lecture proper, for Friday's lecture, is like extra stuff. It's bonus stuff for OAuth 2.0. A lot of it is fundamental to the concept. When you go out there in the real world, you're going to want to use a lot of the stuff we'll talk about today. It's just not required on your homework. So if you're trying to get through the homework, you have questions. If not, I'm just going to rip right into today's content. I'll get through at least a decent chunk of it. Bless you. If there are questions, I'll keep an eye in chat, and you can always raise your hand. But let's keep going, because I want to talk about some of this stuff. I got to at least get to the lecture question content. So here's the authorization code flow. We just went through half of it today, so don't really need a review of that right now. But let's start talking about different attacks and different vulnerabilities, different things that can go wrong with OAuth 2.0. And I want to start with cross-site request forgery. We've, of course, talked about this in one context already this semester. But let's talk about it in another context, in the context of OAuth 2.0. and state. So in the homework, when you're doing the homework, I explicitly say the state is optional. Or no, I don't say the state's optional. I say you don't have to do. I guess it's the same thing. In the Spotify API, in the documentation, it says state is optional but strongly recommended. And I say, nah, let's not worry about that. I want to talk about why it's strongly recommended and why you should absolutely use it. But for the homework, I was trying to, it took 2.5 lectures to get through that stuff. So anything that was technically optional, I was trying to strip out to make it a little bit more approachable. So scope, optional, not doing it. Refresh tokens, not doing it. Those are really the only two things I could really cut and still cover authentication, OAuth properly. But let's talk about what this actually is, because going out there in the real world, you're going to want to know these things. Specifically, state and refresh tokens. We probably won't get beyond that today, but we'll at least get through those two topics. So cross-site request forgery, we talked about this. This is an attacker making cross-site requests for a user, tricking the user into making these cross-site requests. And we talked about it in the context of cookies mostly, making sure that our auth token in that cookie isn't being sent and respected on the cross-site requests. It can be sent, but we had the extra token to make sure it wasn't respected, that we said this token, this cross-site request forgery token, wasn't assigned to this auth token, so I'm not respecting the request. So we want to do something similar here, but let's talk about the attack first. This is a really clever attack. It's pretty fairly complicated for an attacker to pull this off. So let's see what the attacker is going to do if we're not protected using state. So first, the attacker, instead of our app initiating the whole process here, the attacker is going to initiate it by creating their own authorization request. And this authorization request might have actually came from our server. It's up to the attacker what they want to do. But once the attacker goes to our server one time and clicks the button and looks at all the HTTP requests, they can look at that authorization request and see our client ID and our redirect URI, which are the two pieces of information specific to our API or to our app. They can look at the scopes we're asking for too if they want to match that as well. But they can match everything to do with our request. These authorization requests are not private or secret or anything. Everything is out there in the open. An attacker can spoof an authorization request. It's not even spoofing. It's a legit request. They can just create a legit request for our app. So that's what they're going to do. They're going to create a request with their account. They're going to authenticate with the third-party API with their account, which is legitimate. I mean, they're an attacker, so maybe not. But it's an actual account on the API. They're going to use our client ID and our redirect URI to make that request. They're going to click agree, of course, and they're going to get an authorization grant that's linked to their account. Now, to the API, nothing at all is suspicious here. There's no way for the API to tell that our server wasn't involved. And in fact, our server might have been involved. Like the attacker can just click our button. If they don't want to make their own HTTP request, they just click our login with button, and it generates a legit thing that's exactly what they're after anyway. So this could actually be 100% legit at this point. The attacker is going to get the authorization grant, which is a redirect for the attacker to be redirected to our redirect URI. And it has a code, an authorization code, for the attacker's account and for our app. So it's allowing our app to access the attacker's account on the API. And the attacker is going to say, well, I'm not redirecting. I'm just going to take this redirect. I'm not going to actually redirect. So they're not doing this in a browser. They're going to do it in like a Python script or whatever they're using. And they're going to take that URL with the code in it, the redirect URI and the code in a query string, and put it in their pocket. And they're just going to save that and not head over to our app. They're not going to tell us about it at all. And then they get some sucker to click a link. And this is pretty easy to do in this case. All the attacker has to do here is get this user, any victim, to click any link. And that link is going to be the redirect URL, containing the redirect URI and that authorization code for the attacker's account. So this could be a link. It's going to be a link to our app. So it's going to be like ourapp.com. It's going to look completely legit. And ideally, this user is an actual user of our app. That's what the attacker's after. It's going to look completely legit, and it is. It's completely legit. And they click that link, and they're going to be directed to our app because it's a link to our app. It's literally a link to our app. If there's a forum somewhere and somebody puts a link to an app that you use, and it's got a big old query string on it, and you're like, I don't know what a query string is. It starts with the app that I use.com, so it's got to be safe, and you click it. Not that hard to get somebody to do this. And there's no same origin policy that's going to help us here because all of these requests, like under the steps 1 through 4, under the natural order of things, they're all third-party requests. Like it's designed to be third-party requests. So nothing's going to save us here. There's no protection in place to do this until we add state to this, of course. We're going to prevent this. The user clicks that link and is sent to our server. Our server gets a request and does what our server do. Our server gets a request at this endpoint. We have it coded to listen on this endpoint for requests that contain a code, authorization code, and a query string. We're going to get a request with an authorization code and a query string. Really convenient? Okay. It's just going to do its thing. Everything looks completely 100% legit at this point. And remember, we don't verify. We don't know anything about the user at this point. Not until we actually access their private data do we know anything about the user. So everything looks great at this point. No reason to be suspicious at all. Then we cache that code in for an access token. And we link that access token. This is where it gets scary. We link that access token to this user. So we don't know anything about the user yet, but we are going to give them an authorization token as a cookie. We're about to do that, and we're going to set it to this user right here. So their account, this user, whenever we see them, we're going to go to their account that we might have just created or updated their account if we were able to identify this user. Say they're logging in with our service and we're giving them an auth token, and then we're using the API not for login purposes, but to actually just use the API. Then we're going to add that API access token to this legitimate user's account that we did verify the identity of. So it's either that or they're creating a new account and we just gave them an auth token as a cookie that links them to an account on our app that's linked to an access token to the attacker's account on the third-party API. So we have a situation where this user's account on our app is associated with an access token that's going to interact with the API to the attacker's account on the API. Now, if the user makes, say this is a bank API, and the user makes a deposit, that deposit goes to the attacker's account. Any private data in general, any private data that this user sends to our app and says, hey, talk to that API for me and send this private data into that API, goes into the attacker's account. The attacker goes to this account. They can't see what's going on over here, but they check their account over here through this third party's app. They go to their app, and they can see all of the all of the victims' private data that they're sending to that API, third-party API, through our app. So very bad situation, but very clever for the attacker to get their legit credentials uploaded as under that user's account. Very scary, very kind of fancy attack. Okay, so let's prevent against this thing, because we don't like this. We want to protect our users. The solution is state. When you go through the Spotify documentation, it says state, optional, highly recommended. This is where it comes into play. When you create this authorization request, instead of just sending the your client ID and your redirect URI and your scopes, you're going to add state to that and send the state as well. State is, I guess, anything. Technically, it can be anything. What it should be is some big, long, random, high-entropy string that's going to uniquely identify this user. So if this user isn't logged in yet, because they might be clicking login with, and you might have been the first time you've ever seen them, give them a cookie that tracks their session, some token in a cookie, like an auth token, but just for tracking purposes, not for login purposes, and then have the state be a hash of that state token. This is what's recommended, or at least suggested by the RFC, is to do that. But any way to uniquely identify this user That's what you want to set as the state. And then when we go through the process, this API is going to know what to expect when it sees that state, and it's going to put that state in the grant, and you're going to verify right here when you get the grant back, is the state that is associated with that grant exactly the state that you gave this user? And the user's coming back to you, you can check their cookie, hash it, and make sure that hash matches the state, or any other way that you have to verify that this was the state that I gave to this user. Then you can verify that there was no attacker involved. If there was an attacker involved, the attacker can get any state that we gave them associated with them, but once we get this from the user, we're going to say, hey, you're not the one I gave this to. Your cookies don't match this state. Like, what the hell's going on here? And the attacker doesn't have to get the state from us. It can generate any state that they want. They can manually craft any of their requests however they want. So whatever we use for state can't be predictable or guessable. It has to be high entropy. It has to be associated with the user. Nothing to do with the user itself, because the attacker can try to get information from the user. Hopefully they can't grab our state cookie that we gave them. But if they can get other information, like their user agent or their IP address, and we have a state that's a hash of those values, for example, they can get those values. So we have to not be predictable. State, 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 state. Okay. So that's protecting our cross-site request forgery attack. And this state is effectively, now I'm going to notice every time I say it. This state is effectively acting the same way as our cross-site request forgery tokens. It's the same thing. We're giving this random value to a user, and only they can use that value. Like, if they do interact with us again, they have to give us that value back again. If they didn't, we suspect that there was another party involved. Refresh tokens. Moving on. So state and refresh tokens, those are the two big ones we want to talk about. And if you are keeping track of the state count, it's probably about to end. We're not going to talk about it during refresh tokens. So it's very common, and the Spotify API does this. You're going to see this all over the place when you're using OAuth 2.0 APIs, is you're going to get a refresh token in addition to the access token when you cash in your authorization grant. And the access token is a short-lived token for Spotify that's 1 hour, and the refresh token is much, much longer-lived token. So the access token usually expires pretty quickly. And then you need the refresh token. What you're going to do is go back to the server with your refresh token and say, hey, my access token expired. I would like a new one, please. Flash them the refresh token, and they'll give you a new access token, and sometimes a new refresh token, though in practice I haven't seen that very often. You'll usually just get a new access token and keep the same refresh token. And refresh tokens don't really make sense if the auth server and the resource server are the same server. If they're on the same server box, refresh tokens are kind of pointless. But when they're separated, and this is the only time I'll separate these and talk about the differences between the two, when they are separated, this is where refresh tokens have quite a few benefits, albeit nothing too earth-shattering. These things, they aren't like the craziest thing, but they do have some benefits. So when we split these up, the authentication server is, you guessed it, in charge of authentication. So anything to do with issuing tokens, issuing codes, the whole steps 1 through 4, that's the auth server. Cashing in the authorization grant for the access token, that's auth server. Everything's auth server except actually using the API. That's resource server's only job, is when you're actually accessing the API, you're going to send them only the access token. The resource server doesn't see anything else, no authorization codes and no refresh tokens, no client secrets. I guess no client ID technically either. They don't see any of the other information. Client ID is public anyway, so who cares? But the resource server doesn't see any of that private information except the access token, only access token, and it'll verify the access token and then serve up private data. So the advantage of refresh tokens, one is security. We're never sending the refresh token to the resource server, which there seems to be like an unspoken assumption in the RFC that this communication with the resource server is going to be less secure than communication with the authentication server, which I'm not completely sold on that, but we'll go with it. Is that the access token is more likely to be compromised, is the kind of hidden assumption during this communication. The one thing I'll grant them is that this communication is probably going to happen much, much, much more often than any of this communication. For example, if a token's expiring once an hour, at most, this refresh token is being sent once every hour. But API access, you could have an app that's making API access for a single user multiple times per second. You might have a lot of requests, so that's a lot of chances for the attacker to get a hold of this thing. So if the access token is compromised, our security is that it's going to expire soon. Not the best thing. It's not the best form of security, but we're at least limiting the amount of time the attacker has to launch their attacks. Even if they get this token right away, they have 1 hour before that token's going to expire, before it's completely useless. It's rendered 100% useless after that. So if it's compromised, it expires, we get a new one, and the attacker would have to compromise another refresh token if they want to keep attacking this person. They don't compromise one access token and have that account, control that account forever. So a little bit, it's something. It's not the best. And then performance, this is a little bit of a better selling point. If we don't have refresh token, if we don't have refresh tokens, if we just had an access token that was a long-lived token, then we want some way to revoke it. So if the attacker compromises a token that lives for a long time, we want to be able to revoke that token. So if we detect that it's compromised, then we're going to not allow access to it anymore, allow access with that token anymore. This is going to involve the resource server going to the authentication server through an HTTP request. The auth server has to make a database lookup, check if that token is valid, and then respond to the resource server. Or alternatively, the resource server could go directly to a shared database and look up to see how that token's doing. And then if the token's still valid, then the resource server goes to the database with the actual data and serves up the request. So where we need only one database lookup, now we have two, double the database lookups. Databases are on disk. Disk lookups are slow. We know from CSE 341, doubling the amount of a slow process is bad for performance, so we don't like that. With refresh tokens, what we can do is make the access token self-contained, so it has all the information we need, so we don't have to do any database lookups. And then the resource server sees the access token, checks without a database lookup if it's valid, usually by having the token be encrypted, then decrypt it with a key that they share with the auth server, decrypt it, verify the token, see who the user is, who the client is, and then respect the request there, which is much, much, much faster. It doesn't require talking to the auth server or a database, and we can verify that token that way.